Hi, I'm Marc Hendrix, back with AIM Geoanalytics. We're here for our Phosphoria webinar. This is a webinar that has been going on for 3 weeks now. This is week number 4. The title of the webinar, of course, is the Permian Phosphoria Formation and equivalent strata in the Northern Rocky Mountains and Great Basin region. So with week 1, we introduced the stratigraphy and the paleogeography of the Phosphoria. Then in week 2, we looked at the petroleum system, particularly some of the geochemical attributes that correlate the Phosphoria oil in Wyoming with Phosphoria source rocks in Idaho. There's a long distance migration story. Last week, we took a look at some outcrop photographs and characteristics of the Phosphoria, mainly in the Meade Peak and the retort depot centers. And we're going to move a little further east this week up onto the Wyoming shelf and have a look at some Phosphoria equivalent lithofacies from core. And here's one core. This is the core we're going to be focusing on mostly this week. This is the Nance Alvarado Unit 26-2. And this is a core that was cut from the southeastern Bighorn Basin. And you can see here that it's got a number of different lithofacies, including some that are oil stained and others that are not. You see some little nodules up here, and these are little chert nodules that we'll talk a little bit about more coming up. Next week, our final week, we're going to summarize the entire webinar. Okay, so again, this week we're going to be looking at examples from Phosphoria core, mainly from the eastern part of the basin. Again, last week, just to put this into perspective, we focused mainly on lithofacies in the Meade Peak, and the retort depot centers, which are located mainly in southeastern Idaho and the western part of Wyoming, and in the case of the retort here in southwestern Montana. So we focused mainly in kind of the central portion, if you will, of the Phosphoria Basin. This week, we're going to move to the far east. And so by far east, we're talking about the Bighorn Basin, and even in the Powder River Basin, we do see Phosphoria equivalent rocks in both of these basins. And we'll be looking at a core in the Bighorn Basin. But before we do that, I want to just point out this core on the right. This is actually a core from the Powder River Basin, and it's from the Middle Lusa Formation, which is Pennsylvania and Permian in age, and older than the Phosphoria. But in this case, it's a really good example of a unit that's been charged with Phosphoria oil. And again, this is oil that is thought to have been generated in the thermal kitchen further to the west, that is mainly in Idaho, southeastern Idaho, and to have migrated long distance probably during Jurassic time when the foreland basin was unbroken, and this Pennsylvanian sandstone could be more or less fully saturated. So there's this long distance migration story that we keep coming up with here, and that long distance migration has left some of these very porous permeable sandstones in eastern Wyoming charged with Phosphoria oil. Okay, so just to remind us of the overall configuration of stratigraphic units within the Phosphoria, this is a cross-section from west to east across the central Rocky Mountain region, showing that as you go from the thicker deposits of organic rich mudstones with a lot of chert here in the west, this is sort of the depot center, if you will, of the Phosphoria Basin that was influenced by oceanic upwelling. As you go to the east, these organic rich fine grain rocks are supplanted by more normal marine carbonates that are enclosed in a couple of different members. The Grandier member is a carbonate, the Franson member, then this Hervé member here, the youngest of the 3 carbonates. We'll be focusing mainly on the Hervé here in the examples of core from the Alvarado unit. As you go further to the east, actually into easternmost Wyoming, these carbonate facies become more and more evaporitic, and they actually are eventually grade into red beds. All right, so let's take a look at some of the core. This again is from the Alvarado Unit 26-2. This is a core of the Phosphoria. In particular, it's mostly cored within the Hervé member of the Phosphoria. And you can see here that there are a couple of photos of the core itself, showing some bidirectional current rippling here, some planar lamination here. On the right, you see what looks to be a patchy saturation of hydrocarbons in this core, and that is the case. You see a little ripple right here. So this is basically the same facies, but in this case, you have a partial oil saturation, and this part of the core is unsaturated with oil. And as far as where we think we are in the depositional system here, again, we're pretty far to the east. We're up onto the shelf here near the paleo shoreline, and we're actually starting to see influence of evaporites, and that is one reason why we see such a patchy distribution of hydrocarbons in this core. That is, the cements that we see in these rocks are themselves quite patchy. Here's an example of one of the patchy cements that we see in this part of the Phosphoria. This is a ripple laminated dolomite waxstone packstone. So it's been completely dolomitized, and you can see there are places where you've got a little bit more cement, and there are places where there's not quite as much cement. Here, looking at the rock in thin section, you see that it's got a number of smaller grains that are for the most part carbonate peloids that have been dolomitized. Looking at a little closer, notice the scale bar here, 100 microns, so 1/10 of a millimeter. We see basically an anhedral mosaic of dolomite crystals that are preserving the ghost-like remains of various skeletal grains. Here's an example of one right here. We interpret this to be a sponge spicule. So this shows this rock's been completely recrystallized from what was probably a limestone to a dolomite. And notice also there are a few isolated sand-sized grains of phosphate here. So we do see a little bit of isolated phosphate. We see isolated spicules, sponge spicules, but for the most part, this is a very dolomitized rock. Here's another example, again from the Alvarado unit 26-2, and you can see here in the shot of the core itself that this part of the core is oil stained, but again, the staining is quite patchy. Looking at the thin section, we can see some portions of the thin section preserve that oil staining, and again, it's very patchy. Here we look at the thin section itself at about 100x. Here's the scale bar in the lower right. And you can see that most of the grains themselves that are making up this rock are indeed carbonate peloids. There are some open pores. Right here's an open pore. This is not oil saturated. This is a cross-polarized image. So this is actually isotropic cement right here. This is not saturation, but actually just interference colors that are basically black. But the point I want to make here with respect to this pore is that it is interpreted to be a moldic pore. You see there are some sort of obvious looking pores that look like they have a grain shape, as well as pores here between these grains. So there seems to be both moldic porosity and interparticle porosity, as well as some intercrystalline porosity at a micro scale. The other thing I want to point out here is notice that projecting into this open moldic pore is a very nicely shaped, that is, euhedral crystal of dolomite. We see a similar relationship here. There's a pore and there's a dolomite crystal projecting into that pore that obviously grew into the open space. And that dolomite is itself overlain by a small crystal of quartz. So we actually have two dolomite crystals, one here, one here. And so the point I'm trying to make is that following the moldic porosity, the development of this moldic porosity, there was at least one dolomite precipitation event followed by at least one silica or quartz precipitation event. So this is suggesting that we have a fairly complicated diagenetic history. Here's one of the more interesting and unusual facies that we see in the Alvarado Core from the Bighorn Basin. It's essentially a chert breccia whereby much of the dolomite has been partially or completely silicified, and that then the entire section has undergone significant amounts of chemical compaction, that is, removal of mass through the development of these pressure solution seams. Oftentimes they're called stylites. So we see a lot of these stylites in this section, particularly in the carbonates. The stylites are not so much shown in the chert nodules, but the chert nodules themselves are oftentimes very significantly brecciated. You can see these fractures here that are in part filled with mobilized hydrocarbons. The other thing to point out, excuse me, in this slide is in thin section, we're starting to see a third mineral here, a new mineral, let's put it that way. So here we're looking at a largely silicified portion of the rock. There's a little bit of late stage dolomite replacement of that silica. And then we have this cobalt blue mineral here. This is a cross polarized image. So these are interference colors. This is a late stage patch of anhydrite that's now partially replacing the host rock. So we see a little bit of it here and here. We again see then this is a fairly complicated diagenetic history. Here's a perigenetic overview that I put together after looking at the Alvarado Core and a number of different thin sections and trying to document the various stages of diagenesis and the various events that took place during that diagenesis. And so this chart, which is fairly standard, is color coded. So the yellow bars here represent events that have to do with deposition happening early in the diagenetic or early in the history of these rocks. The blue events are events that are interpreted to have created porosity. So either dissolution of grains or dissolution of cement or some event that was able to create porosity. In contrast, the red bars here show events that are associated with the reduction or the destruction of porosity. So these mostly are mineral cementation and or replacement events. And each of these is put in the context of the charging of these rocks by mobilized hydrocarbons. Again, we think this is that long distance migration. And so in summary, what you can see is that early in the history of these rocks in the eastern part of the Phosphoria Basin, there were a number of pore producing diagenetic events, mostly through dissolution. But then following the introduction of hydrocarbons, there are a number of events that have ultimately destroyed or reduced that porosity. And a lot of these likely have to do with the transition from really deep burial to a situation following laramide partitioning of the foreland basin, where these rocks have been uplifted and maybe locally have subject themselves to meteoric influences. And so that meteoric water likely has resulted in the dissolution and reprecipitation of a lot of these evaporitic minerals, particularly anhydrite. All right, so to summarize here, this week we came out of the basin center and we were focusing on some of the carbonate and evaporite facies in the eastern part of the Phosphoria Basin, particularly in the Bighorn Basin. Here's an example of a normal marine carbonate that's on sort of in the central Wyoming region, and an example from our Alvarado Core of a very dolomitized equivalent further up onto the shelf. Both cases there are hydrocarbons present, but in the case of the more shelfal deposits, the diagenetic history seems to have been much more complicated. Okay, so that's it for this week. Next week, we're going to summarize the entire webinar. And so until then, this is Marc Hendrix from AIM Geoanalytics. See you next week.